Time only flows one way in our lives. A glass shatters on the floor and never reassembles itself. Our memories are filled with the past, never the future. This irreversible arrow of time feels like the most basic rule of reality. Yet, when we look at the universe's fundamental laws, from Newton's mechanics to Einstein's relativity to the equations of quantum physics, something strange happens. These laws are perfectly time-symmetric. They work just as well running backwards as forwards, so we are left with a profound paradox. If the universe's deepest rules do not care about the direction of time, why does our reality have such a definite, one-way arrow? The answer is not written in the laws of motion, but in a deceptively simple statistical concept called entropy. By the end of this exploration, you will understand how the relentless growth of disorder in the universe carves the very path of time itself, linking the moment a cup breaks to the origin of the cosmos. How could something as ordinary as a mess hold the key to time's greatest mystery? This perfect symmetry at the heart of physics creates an astonishing thought experiment. Take a single moment in the life of a simple system, like two billiard balls colliding on a perfectly smooth, frictionless table. In a pristine recording, you would see them approach, strike with a sharp click, and recoil, rolling away with new speeds and directions. Now play that recording in reverse. The balls roll backward, meet, touch, and separate, returning exactly to their starting positions. The reversed film looks just as physically valid as the original. There is no law of physics violated in the backwards version. The equations that describe that collision, whether Newton's or those of quantum mechanics, treat both directions of time as equally real. They are time-symmetric. This holds true not just for two balls, but for every single interaction between fundamental particles. If you could magically reverse the velocity of every atom in the universe, the entire cosmic movie would play in rewind. Planets would roll backward in their orbits, light would retreat into stars, and broken glasses would rise from the floor and reassemble. According to the bedrock laws, this is just as permissible as the forward version we experience. So the puzzle deepens. Our reality feels like a river flowing relentlessly in one direction, yet the universe's most fundamental rules describe a placid lake, perfectly still and indifferent to which way you look across it. The arrow of time is not etched into the gears of reality. It must be painted onto the canvas by something else entirely, a principle that guides the universe's story even when its laws do not. The river of time must have its source, and physicists found it not in force or energy, but in a subtle, statistical tendency. This is where entropy enters the story. At its heart, entropy is simply a measure of disorder, but to understand its power, we need to look a little deeper. Think of any familiar object in its organized state, like a freshly made bed with smooth sheets and plumped pillows. There is essentially one way, or just a very few specific ways, for the bed to look perfectly made. Now consider that same bed after a night's sleep, blankets tangled and pillows askew. There are countless different arrangements of those sheets and blankets that all look equally messy. The messy state is not special, it is just vastly more common. It represents a huge number of possibilities. This is the core idea. Entropy counts the number of microscopic arrangements, called microstates, that all result in the same overall macroscopic appearance. A tidy room has low entropy because only a few specific arrangements of everything in it look tidy. A messy room has high entropy because an enormous number of different arrangements all look messy. The universe, in a sense, is constantly moving from the rare, specific arrangements to the common, generic ones. This is not a law about what must happen, but about what is overwhelmingly likely to happen. It is a statistical certainty. This tendency is codified in one of physics' most profound principles, the Second Law of Thermodynamics. It states a simple, directional rule. In any isolated system, a system that does not exchange energy or matter with its surroundings, the total entropy never decreases over time. It either stays the same or, far more commonly, it increases. Here at last we have a law that points forward. It gives us an arrow, but this only sharpens our original paradox. If the fundamental laws are reversible, why does this statistical law seem so absolute? Why does the universe have such a powerful preference for disorder? The bridge between these two worlds, the reversible laws of particles and the irreversible flow of time we see, was built by a man wrestling with profound ideas in the late 19th century. His name was Ludwig Boltzmann. While others saw the second law as a mysterious, absolute command of nature, Boltzmann had a different, more profound insight. He realized that entropy was not about what must happen, but about what is overwhelmingly likely to happen. It was a matter of statistics and probability, not force. He proposed that any macroscopic state, like a hot cup of coffee or a cold room, is really just the average appearance of a hidden, chaotic dance of countless atoms. For every way a system can look to our eyes, there are a staggering number of specific arrangements, or microstates, of all its particles that would create that exact appearance. Boltzmann's genius was to link entropy directly to counting these possibilities. His famous equation, etched into his memorial, is deceptively simple. Entropy equals a constant times the logarithm of the number of microstates. In plain language, the more microscopic ways a system can be arranged while still looking the same to us, the higher its entropy. This is the statistical key. Think back to the tidy room versus the messy room. The messy state has astronomically more microstates. If every atom is just moving randomly, the system will almost always be found in one of the vast number of messy, high-entropy arrangements, simply because they are so much more common. The second law, then, is not a fundamental rule like gravity. It is a statement of overwhelming odds. It is staggeringly likely that entropy will increase, so likely that for any system of real-world scale, it becomes a practical certainty. But crucially, in Boltzmann's view, it is not impossible for entropy to decrease. It is just incredibly, mind-bogglingly improbable. You could wait longer than the age of the universe and never see all the air molecules in your room spontaneously crowd into one corner. But it is not forbidden by the particle laws. This statistical interpretation was the missing link. It showed how trillions upon trillions of tiny, reversible interactions could collectively give rise to the irreversible, one-way arrow of time we experience at our scale. The universe moves from order to disorder not because it must, but because disorder is where almost all the paths lead. Boltzmann's statistical insight reveals the true nature of time's arrow. It emerges not from a command, but from the quiet tyranny of probability. Let's make this concrete. Imagine a simple, sealed box divided by a removable partition. On one side, we have a gas like the air in this room, confined to a single corner. Every atom is bouncing around, but they are all trapped in that small, ordered space. This is a low-entropy state. Why? Because there is only one specific, microscopic arrangement, or a very small set of them, where every single atom happens to be on that one side of the box. Now we carefully remove the partition. What happens next is a story told by statistics. The atoms, governed by those perfectly reversible laws of motion, begin to bounce and collide. With the entire volume of the box now available to them, they will naturally spread out. Soon, the gas fills the entire container uniformly. This is the high-entropy state. The key is to understand why this is inevitable. It is not because the laws of physics push the atoms apart. It is because the number of microscopic arrangements where the gas is spread evenly throughout the box is astronomically, unimaginably larger than the number of arrangements where it is all crammed into one corner. If every atom's motion is random, the system is almost certain to be found in one of the overwhelmingly common, spread-out configurations. The transition from order to disorder is simply the system moving from a rare arrangement to a common one. Now play this movie in reverse. You would see a box full of uniformly spread gas suddenly, spontaneously, and for no apparent reason have all its atoms coordinate their movements. They would all bounce and careen in just the right way to herd themselves perfectly back into one corner, leaving a perfect vacuum everywhere else. This reversed sequence obeys every single microscopic law of physics. Each atom's path, when reversed, is a valid trajectory. So why do we never see it? Because the odds are so vanishingly small, they are effectively zero. You would have to wait many, many times longer than the current age of the universe to witness such a spontaneous coordination by chance. This is the irreversible arrow. The forward direction of time is simply the direction in which entropy increases. We remember the past because it was a state of lower entropy, and we anticipate a future of higher entropy. The gas spreading in the box is not just a metaphor. It is a microscopic model of every irreversible process, from cream mixing into coffee to the fading of a memory. The universe is moving from a specific, improbable past toward a generic, probable future. But this raises a monumental new question, one that reaches back to the very beginning of everything. If our arrow of time depends on starting in a state of incredibly low probability, how did the universe find itself in such an ordered starting condition in the first place? Boltzmann's brilliant statistical answer leaves us staring at an even deeper cosmic mystery. If the arrow of time is simply the universe moving from a rare, ordered past toward a common, disordered future, we must ask the most fundamental question of all. Where did that rare, ordered past come from? What set the initial condition? To find the source of time's river, we must look back to the very beginning of everything we know, to the event that gave our cosmos its first moment, the Big Bang. Our observable universe began not in chaos, but in an astonishing state of exquisite order. Think of it as a cosmic seed of unimaginable density and temperature, a primordial fireball. But here is the crucial, counterintuitive detail. This early universe was remarkably smooth and uniform. The energy was distributed almost perfectly evenly across space. In terms of gravity, which would soon become the dominant force shaping the cosmos, this smoothness represents an incredibly low entropy state. Why? Because gravity loves clumps. A universe where all matter is spread out evenly is like that gas confined to one corner of the box. It is a very specific, improbable arrangement. The high entropy state for gravity is one of maximum disorder, a universe collapsed into black holes and scattered debris. Our universe did not start that way. It started smooth, a condition of fantastic simplicity and order. This single, extraordinary fact, the Big Bang's low gravitational entropy, is the ultimate boundary. It is the past condition that everything flows from. It provides the temporal asymmetry. Time's arrow points relentlessly away from this singular moment of low entropy, driving the universe toward the mixed, clumped, and increasingly disordered states we see evolving all around us. The expansion of space, the formation of the first stars, the birth of galaxies, all of these are the direct result of the universe unraveling from that initial, tight knot of order. So the ultimate answer to why we remember yesterday and not tomorrow is written in the first flash of cosmic light. Our past is special because it connects directly to the most special state of all, the beginning. Yet this realization feels less like an answer and more like the opening of a grander, more perplexing door. If a low entropy beginning is so statistically improbable, why did it happen at all? The smoothness of the Big Bang appears not as an explanation, but as the greatest cosmic puzzle of them all. This smooth beginning is the very heart of the mystery. We often think of order as structure, like a neatly stacked bookshelf or a spiral galaxy. Disorder, then, would be a chaotic jumble, but gravity turns this intuition completely upside down. To understand the universe's true starting point, we must distinguish between two kinds of entropy, thermal and gravitational. The early universe was a searingly hot, dense soup of particles. In terms of heat and radiation, it was in a state of near-perfect thermal equilibrium, a very high entropy state for energy. Everything was mixed together uniformly. Yet for gravity, this uniform smoothness is the ultimate state of order, the lowest possible entropy. Gravity is a force of attraction. It wants to gather things together. The most disordered, high-entropy state for a gravitational system is not a smooth cloud, but a wildly clumped and complex one, a final state of black holes and scattered remnants. Our universe began in the opposite condition, a remarkably smooth and even distribution of matter and energy. This was an incredibly specific, improbable starting point. From this pristine beginning, gravity got to work. The tiny quantum ripples in that smooth fabric, imperfections smaller than an atom, became the seeds for everything we see today. As the universe expanded and cooled, gravity amplified those tiny flaws. Matter began to clump around them. Vast clouds of gas coalesced, fragmented, and ignited into the first stars. Those stars gathered into galaxies, and galaxies into clusters. This grand cosmic structuring, the birth of every star and planet, is not the universe becoming more ordered. It is the universe's gravitational entropy increasing. It is moving from the rare, smooth state toward the vastly more probable, clumpy state. The formation of a complex galaxy from a smooth cloud of hydrogen is, in gravitational terms, like watching a gas spread out to fill a room. It is the system exploring the enormous number of ways to be lumpy and structured, so there is no paradox. The universe is not creating order from chaos. It is creating gravitational disorder from gravitational order. The stunning spiral of a galaxy is not a monument to cosmic tidiness. It is a fingerprint of the universe relentlessly unraveling toward its most probable and ultimately final form. Our own minds are living proof of this cosmic tendency. We do not just observe time's arrow, we feel it. This is the psychological arrow of time, the undeniable flow of our consciousness from what we call the past toward what we call the future. It is the feeling that yesterday is fixed and gone, while tomorrow is open and unknown. But this is not some mystical property of the mind. It is a physical process, intimately tied to the same statistical rule that governs the spreading of gas. Our perception of time is rooted in memory. To remember something is to have a record of it, a specific pattern in our brain that was formed by a past event. The formation of that memory is not a magic trick. It is a biochemical event. Every thought, every new memory involves neurons firing, signals traveling, and chemicals being released. This work requires energy. That energy is ultimately dissipated as a tiny amount of heat, and the dispersal of energy as heat is, by definition, an increase in entropy. Think of the moment you learn a new fact. As the neural connections form, your brain is doing work. That work generates a minuscule amount of warmth, a tiny dispersal of energy into the surrounding tissue. This is entropy increasing. The memory itself, the ordered pattern of neurons, is the record of that process. We remember the past precisely because the past was a state of lower entropy that led, through an entropy-increasing process, to our current brain state. The memory is the scar left by the universe's march toward disorder. This is why we cannot remember the future. For your brain to contain a memory of an event that has not yet happened, it would mean the entropy-increasing process of forming that memory would have to occur before the event itself. This would require a spontaneous, miraculous decrease in entropy, a coordination of particles even more unlikely than all the air in a room gathering in one corner. Our consciousness is not riding the arrow of time, it is woven from it. The feeling that time flows is the feeling of our own brains constantly recording the universe's journey from order to disorder, one irreversible memory at a time. This deep connection between memory and entropy reveals another cornerstone of our reality, the very structure of cause and effect. We live in a world where causes always come before their effects. A lit match causes a fire, a spoken word causes a sound. This seems so obvious it hardly needs stating. Yet, like the arrow of time itself, this causal order is not guaranteed by the fundamental laws of physics. It too is a gift of entropy. Think of a simple line of dominoes standing on end. You tip the first one, it falls, strikes the second, which strikes the third, and so on down the line. This is a classic causal chain. The fall of the first domino is the cause of the fall of the second. But what is physically happening? Each collision transfers energy, but not perfectly. A tiny amount of energy is lost with every click, dissipated as sound waves that warm the air and as a little bit of heat from the friction at the point of contact. This dispersal of energy is once again an increase in entropy. The ordered, upright state of the dominoes represents potential energy, a specific configuration. The fallen, scattered state represents that energy having been released and spread out into the environment. The cause, the initial push, exists in a moment of lower entropy than the final, silent result. Now play this movie backwards. You would see a bizarre spectacle. Dominoes lying flat would spontaneously right themselves, one after another, in a perfect wave. The sound waves in the air would converge from all corners of the room, focusing their energy precisely at each domino's edge to provide the exact push needed to lift it. This reversed sequence gathers dispersed energy, concentrating it back into the orderly, upright potential of the dominoes. It represents a dramatic, spontaneous decrease in entropy. While every single atomic interaction in that reversed film is technically valid by the laws of motion, the coordinated sequence as a whole is so astronomically improbable we know we will never witness it. This is why we never see effects precede their causes. An effect, like a fallen domino or a memory in your brain, is almost always a state of higher entropy than its cause. For an effect to happen before its cause, entropy would have to locally and miraculously decrease, coordinating countless particles to reverse the natural flow of energy. The causal arrow of time is not a separate rule, it is the thermodynamic arrow in disguise. We experience a universe where causes lead to effects because that is the only direction in which the story of increasing disorder can logically be told. Yet this statistical view of time leaves a haunting theoretical possibility. If the universe is governed by reversible laws and probability, could the arrow ever reverse itself? Could the universe, after eons of increasing disorder, somehow find its way back to order? This question leads us to a profound mathematical idea known as Poincaré's recurrence theorem. In essence, it states something astonishing about a finite, isolated system, like a box of gas or even a hypothetical closed universe. If the system's motion is bounded, meaning particles cannot fly off to infinity, and if we wait long enough, an almost unimaginably long time, the system will eventually return to a state that is arbitrarily close to its initial configuration. Every atom will come back to nearly the same position and velocity it started with. In principle, this means the gas that spread out in our box could, by pure chance, spontaneously gather itself back into one corner. Entropy would decrease, the arrow of time for that system would appear to point backwards. The timescales involved here are not just long, they are incomprehensible. For a system as simple as a dozen particles bouncing in a box, the recurrence time might be measured in seconds or years. But for any macroscopic system, the number of possible microstates is so colossal that the time needed for a return to a low-entropy state becomes staggeringly vast. For something like all the air molecules in a room to spontaneously gather in one corner, the expected wait time is many, many orders of magnitude longer than the current age of the universe. We are talking about numbers so large they have no meaningful connection to human experience, durations that make the lifetime of stars seem like a blink. So, does this theorem dismantle everything we've built? Does it mean our arrow of time is an illusion, just a temporary phase in an eternal cycle of order and disorder? In a purely mathematical sense, it suggests that possibility, but in a practical, physical sense, it changes nothing about our reality. The recurrence time for our observable universe, if it is finite and closed, is so astronomically long that it has no bearing on the cosmos we inhabit or the lives we lead. Our universe is only 13.8 billion years old, a mere instant on the timescale required for any meaningful recurrence to even be conceivable. The arrow of time we experience is not an absolute, unbreakable law etched into the fabric of reality. It is an emergent, statistical certainty over the timescales that matter to us. It is the overwhelming, dominant story written by probability for a universe that began in a special, low-entropy state. Poincaré's theorem doesn't threaten our understanding, it refines it. It tells us that the second law is not about never, but about almost never within the lifespan of everything we know. This realization shifts our perspective from seeing time's arrow as a fundamental command to understanding it as the most probable path through an ocean of possibilities, a path our universe has been faithfully following since its first moment. But if entropy's rise is merely a matter of overwhelming odds, could a clever enough mind find a loophole? In the 1870s, the great physicist James Clerk Maxwell proposed a brilliant thought experiment that seemed to do just that. He envisioned a tiny, intelligent being, later called Maxwell's demon, stationed at a microscopic door between two chambers filled with gas. Initially, both chambers are at the same temperature. The demon's job is simple. It watches the molecules approaching the door. When it sees a fast-moving, hot molecule coming from the left chamber, it opens the door to let it pass into the right. When it sees a slow-moving, cold molecule coming from the right, it lets it pass into the left. It slams the door shut for all other molecules. Over time, this selective sorting would have a dramatic effect. The right chamber would fill with fast, hot molecules heating up. The left chamber would fill with slow, cold molecules cooling down. A temperature difference would emerge from uniformity, all without the demon doing any physical work like pushing a piston. This appears to be a direct violation of the second law. Order has been created from disorder, and entropy has decreased, seemingly for free. For nearly a century, this demon haunted the foundations of physics, a ghost in the machine that suggested information and intelligence could defeat the universe's tendency toward disorder. The resolution to the paradox came from understanding that the demon itself is not a magical outside observer. It is a physical part of the system. To do its job, the demon must acquire information. It must see or otherwise measure the speed and position of each approaching molecule. That act of measurement is not free. It requires an interaction. The demon, whether a microscopic creature or a sophisticated nanomachine, needs a way to detect the molecule, perhaps by bouncing a photon of light off it. That interaction transfers a tiny amount of energy and disturbs the molecule ever so slightly. More importantly, for the demon to store and process that information, to decide when to open the door, it needs a physical memory. It could be a notebook, a row of switches, or a pattern in its own structure. Resetting that memory, clearing it to make room for new data, is a physical process that dissipates energy as heat. When physicists finally did the full accounting, they found the total entropy increase from the demon's measurement and memory erasure processes was always greater than the entropy decrease it achieved by sorting the molecules. The demon does not break the second law, it fulfills it. Its attempt to create order locally only generates more disorder globally within its own mechanisms. This profound resolution forged an unexpected link between the abstract world of information and the concrete reality of thermodynamics. Information is physical. Gaining knowledge about a system and then discarding that knowledge has a real, unavoidable thermodynamic cost. The demon's failure is our universe's guarantee. There is no free lunch, not even for a mind that knows the position and speed of every atom. Maxwell's demon was finally defeated by its own need to remember. This key insight, that information is not a ghost in the machine but a physical part of the world, leads us to a profound and elegant limit. It is called Landauer's principle, and it states a simple, inescapable fact. Erasing information is a physical act that inevitably increases entropy. Think of the demon's memory, perhaps a tiny notebook where it jots down whether each molecule was fast or slow. To keep sorting new molecules, the demon must eventually clear that notebook, resetting its pages to blank. That erasure is not a magical deletion, it is a thermodynamic event. When you irreversibly erase a single bit of information, like flipping a switch from a known state to a zero, you must dissipate a minimum amount of energy as heat into the environment. This is not a limitation of our current technology, it is a fundamental law of physics. The act of forgetting has a concrete, measurable cost. The universe demands a payment in disorder for every bit of certainty you destroy. This principle forever links the abstract world of information to the concrete flow of time. Creating a memory might be reversible in theory, but choosing to forget, to reset your knowledge to a blank slate, is an intrinsically irreversible step. It is a one-way street paved with dissipated heat, so the demon's entire operation is doomed. The slight decrease in entropy it achieves by sorting hot and cold molecules is always outweighed by the greater increase in entropy produced when it must clear its own memory to continue its work. There is no clever loophole. Information is physical, and its manipulation is bound by the same relentless statistical tide that governs everything else. Every time you delete a file on your computer or a thought from your mind, you are participating in this universal process, paying a tiny thermal toll that reinforces the arrow of time itself. The demon's failure is a triumph of understanding, showing that even intelligence cannot escape the thermodynamic narrative of our universe. The universe is not just growing more disordered, it is literally growing. Space itself is stretching, carrying galaxies away from one another in a relentless expansion that began with the Big Bang. This cosmic expansion presents another compelling candidate for the master of time's arrow. Could it be that the stretching of space, not just statistics, is what truly defines past from future? The idea is elegant in its simplicity. Expansion provides a clear, cosmic scale asymmetry. The past was hot, dense, and small. The future is cold, diffuse, and vast. This progression from a compressed beginning to an ever-spreading emptiness gives us an obvious direction that feels intrinsically linked to time. More than that, some physicists argue expansion is the essential engine that allows entropy to increase at all. Think of our box of gas. If the box itself were constantly, slowly growing larger, the gas would have ever more room to spread into. It would never truly reach a final, static equilibrium of maximum entropy because the goalposts are always moving. The expansion of space, in this view, continuously pulls the universe away from equilibrium, providing an endless frontier for disorder to explore. It creates the room needed for entropy to keep rising. Without this stretching, the argument goes, the universe might eventually reach a state of maximum disorder, a lukewarm soup where nothing happens, and the arrow of time would effectively fade away. Expansion keeps the story going, yet is expansion the true driver, or is it just the stage? To find out, we must perform a thought experiment in reverse. Imagine for a moment a universe that is not expanding but contracting. Gravity pulls everything back together. Space shrinks. Galaxies hurtle toward a final, crushing singularity. In such a cosmos, would time run backwards? Would cause and effect reverse? The surprising answer from statistical mechanics is no. The arrow of time would still point from a lower entropy past to a higher entropy future. Even in a collapsing universe, you would need that special, low-entropy boundary condition at the beginning to set the temporal direction. The contraction would simply be the backdrop against which the statistical story of increasing disorder plays out. Processes like stars shining, life thinking, and memories forming would still increase the total entropy of the universe, even as everything crunches together. The expansion of our universe is therefore not the creator of time's arrow, but its magnificent enabler. It is the grand, architectural feature that ensures the cosmic journey from order to disorder has the space and time to unfold in the spectacular way we see. It sets the stage, but the play itself is still written by probability, directed by the initial low-entropy state of the Big Bang, so we are left with a cosmic collaboration. The smooth beginning gave us the arrow, the expansion gives it a highway on which to travel, and we, conscious beings formed from stardust, are the witnesses who feel its relentless, one-way flow in every moment of our existence. If expansion is the stage for time's arrow, then black holes are its most dramatic actors. These gravitational monsters are not just cosmic vacuum cleaners, they are the ultimate entropy sinks, playing a starring role in the universe's long-term thermodynamic story. To understand why, we must revisit our definition of disorder. For a gas, entropy is about the number of ways molecules can be arranged. For a black hole, the concept becomes something far more profound and geometric. In the early 1970s, a young physicist named Jacob Bekenstein made a startling proposal. He argued that a black hole's entropy is not hidden inside its mysterious core, but is written on its boundary, the event horizon. This is the point of no return, the spherical shell around the black hole from which not even light can escape. Bekenstein suggested that the entropy of a black hole is directly proportional to the area of its event horizon. The larger the black hole, the greater its surface area and the more entropy it contains. This was a revolutionary idea, linking the abstract concept of information and disorder to the very geometry of spacetime. Stephen Hawking initially resisted this idea as it seemed to challenge thermodynamics, but his own later work would cement it into law. Hawking discovered that black holes are not truly black. Due to subtle quantum effects at the event horizon, they slowly radiate energy, a faint glow now called Hawking radiation. This radiation has a temperature. And if a black hole has a temperature, it must obey the laws of thermodynamics. Hawking's calculations confirmed Bekenstein's intuition, giving the exact formula. A black hole's entropy is 1/4 of the area of its event horizon, measured in tiny units called Planck areas. The numbers are staggering. A single stellar mass black hole, formed from a collapsed star, contains more entropy than all the particles in the observable universe combined before its formation. The act of a star collapsing into a black hole is not just a dramatic death. It is the single most efficient entropy-generating process we know. It takes the complex, but relatively low entropy, structure of a star and transforms it into the ultimate high-entropy object, where almost all information about what fell in is lost to the outside universe, save for its mass, spin, and charge. This represents a colossal, irreversible leap in gravitational disorder. So black holes are not exceptions to the second law, they are its ultimate expression. They are perhaps the highest entropy states that matter can achieve, but the story does not end there. Hawking radiation introduces a fascinating, slow-motion finale. Because a black hole radiates, it loses energy. Since energy and mass are equivalent, it slowly loses mass. Over unimaginable eons, a black hole will evaporate, becoming smaller and hotter until it presumably vanishes in a final burst of energy. This evaporation process is critical. The Hawking radiation that leaves the black hole carries entropy away into the wider universe. Detailed calculations show that the total entropy, that of the radiating black hole plus the entropy carried away by the radiation, always increases. Even the death of a black hole obeys the relentless rule. In the far, far future, as the universe expands toward cold darkness, black holes may be the last significant structures, slowly boiling away and seeding the void with their final entropy. They are not destroyers of time's arrow, but its guardians, ensuring that the universe's journey from order to disorder continues on the grandest scales all the way to the end. The logical conclusion of this relentless drift toward disorder is a future of profound and permanent stillness. If the arrow of time is defined by the increase of entropy, then its final destination must be a state where entropy can increase no more. This ultimate end is known as the heat death of the universe. It is not a dramatic explosion or a sudden collapse, but the quietest possible finale. Picture our universe on a timescale so vast it makes the current age of stars seem like the first spark of a match. The expansion of space continues, carrying galaxies ever farther apart. Over eons, the last stars will exhaust their fuel and fade to darkness. Black holes, those titans of entropy, will themselves slowly evaporate through Hawking radiation, leaving behind only a faint, cold mist of particles and energy. The universe will become a near-perfect vacuum, unimaginably large and almost entirely empty. The temperature everywhere will approach absolute zero, but not quite. A faint, uniform background warmth will remain, the last remnant of all the energy ever released by every star and every process. This is the heat death. In this state, the cosmos reaches thermodynamic equilibrium. Energy is spread so perfectly thin and evenly that no place is warmer or colder than any other. No concentration of energy means no gradients, and without a gradient, no work can be done. A universe with no temperature differences is a universe with no engines. Nothing moves from high to low because everything is already at the same low level. It is a cosmic flatline. In this final configuration, entropy has reached its maximum possible value. There is simply nowhere left for disorder to go. The system has explored every conceivable microscopic arrangement and settled into the most generic, most probable state of all, a uniform sea of dilute particles and radiation. This is the ultimate triumph of statistics, the final, frozen expression of probability. And here, the arrow of time itself fades away. With no net increase in entropy possible, there is no longer a preferred direction for physical processes. Microscopic fluctuations will still occur as particles randomly jostle. Occasionally, by sheer chance, a tiny pocket of space might spontaneously see a brief, local decrease in entropy, like a single ripple on an otherwise motionless ocean. But these fluctuations are random and isolated, with no connection to a larger flow. There is no consistent direction from past to future because the macroscopic state never changes. Without change, there is no time as we understand it, only an endless, featureless now. The heat death is not a violent end, but a gentle fading into uniformity. It provides a grim yet profoundly logical bookend to the story that began with the low-entropy singularity of the Big Bang. Our universe's entire epic, from the first flash of light to the rise of consciousness, is the story of the cosmos moving between these 2 points, from a rare and special beginning to the most probable and final state. Our experience of time, of cause and effect, of memory and anticipation, is the living narrative of that singular journey. But what about the quantum world, the strange and counterintuitive realm that underlies everything? Does it hold a secret arrow of its own? The fundamental equation of quantum mechanics, the Schrödinger equation, is just as time-symmetric as Newton's laws. If you take a quantum wave function, the mathematical object that describes a particle's fuzzy cloud of possibilities, and run its evolution backwards, the equation is perfectly happy. There is no inherent quantum arrow pointing forward, yet we all know about the famous measurement problem. When we observe a quantum system, like an electron that could be spinning up or down, its wave function seems to collapse. It picks one definite state from a haze of possibilities. This feels profoundly irreversible. Once you've seen the electron spinning up, it's as if a door has slammed shut on all the other potential outcomes. But is this collapse a real physical process that breaks time symmetry? Many physicists now think the answer is no. They see collapse not as a fundamental event, but as an epistemic shift, a change in our knowledge, not in the universe itself. The key to understanding this shift is a process called quantum decoherence. Imagine a single, isolated atom in a superposition, existing in two states at once. This fragile quantum weirdness can only be maintained if the atom is perfectly shielded from its environment. The moment it interacts with even a single photon of light or a stray air molecule, something critical happens. Information about the atom's state leaks out into the environment. That photon scatters off the atom in a way that depends on which state it is in, and then flies away, carrying that information into the wider world. This process is not a magical collapse, it is an entanglement. The atom becomes inextricably linked with its environment. From the perspective of anyone or any measuring device that tries to look at just the atom alone, the other entangled possibilities become effectively invisible. They are still there in the full quantum description of the universe, but for all practical purposes, the atom now behaves like a classical object with a definite state. And here is the crucial link to our main story. Decoherence is not a gentle process. It is messy, irreversible, and explosive. When that quantum system interacts with its environment, it disturbs countless other particles, sending ripples of information outwards in a way that can never be perfectly undone. This irreversible scrambling is at its heart an entropy increase. The pure, low-entropy quantum state evolves into a high-entropy, entangled mess. So quantum mechanics does not provide a new, magical source for time's arrow. Instead, it seamlessly integrates into the thermodynamic framework we've already built. The apparent irreversibility of measurement and the emergence of a classical world from quantum possibilities are both consequences of decoherence, which is itself a powerful engine of increasing disorder. The quantum realm obeys the same statistical tide as the rest of reality. Its mysteries unfold along the one-way street carved by entropy, from the rare and specific toward the common and probable, just on an unimaginably small scale. But the quantum realm holds one final, profound symmetry that takes our understanding of time to its absolute limit. It is called CPT symmetry, and it is considered a sacred theorem of modern physics. C stands for charge, reversing the electric charge of every particle, turning an electron into a positron. P stands for parity, which flips the spatial coordinates, turning the universe into its perfect mirror image. And T, of course, stands for time reversal. The stunning claim of CPT symmetry is that the combined application of all three transformations must leave the laws of physics completely unchanged. If you could take the entire universe, flip its charge, mirror its space, and reverse the flow of time, everything would behave exactly as it does in our reality. This is not just a suggestion, it is a bedrock principle derived from our deepest theories. Its power hints at something extraordinary. While our universe clearly violates individual C, P, and even T symmetry in certain interactions, the combined CPT must always hold. This leads to a breathtaking, if highly speculative, thought. If the laws are truly symmetric under this triple reversal, then the Big Bang, our singular moment of low entropy, might not have been the only possible outcome. Perhaps it was not a unique beginning, but a branching point. On one side of this cosmic moment, a universe like ours emerged, with matter dominant and time flowing forward into increasing entropy as we perceive it. But what about the other side? Could there be, in a mathematical sense, a mirror universe emerging from the same primordial event, but obeying the CPT transformation? In such a universe, antimatter would be dominant, spatial handedness would be flipped, and crucially, the arrow of time would point in the opposite direction relative to our own. From our perspective, that universe would be evolving backwards in time, with entropy increasing toward what we call its past. For beings in that universe, their experience would be just as consistent and real as ours. They would remember what we call the future and anticipate what we call the past, all while feeling their own time move forward from their low entropy beginning. This is not science fiction, but a logical possibility permitted by the symmetry of the laws. It underscores with stunning clarity that the arrow of time is not woven into the fabric of physics itself. It is painted onto the canvas by a single, extraordinary boundary condition, the low entropy state of the Big Bang. That initial moment of exquisite order is the master switch. It chose our direction of time from a set of symmetric possibilities. Without that special starting point, the concepts of past and future, cause and effect, memory and anticipation would have no meaning. The universe would be a static poem of perfect symmetry with no story to tell. Our reality, with its one-way flow, is the story. This ultimate dependence on a single, special starting point has a name in modern physics and philosophy. It is called the past hypothesis. Philosopher of science David Albert coined this term to describe the one fundamental assumption we must make to explain our entire experience of time. The past hypothesis is simply the statement that the universe began in a state of extremely low entropy. It is not a law derived from deeper principles. It is a postulate, a boundary condition we must add to the otherwise time-symmetric laws of statistical mechanics. Think of it as the initial setting on a cosmic machine. The machine's gears, the dynamical laws of physics, are perfectly reversible. They could run the universe forward or backward with equal validity. But the past hypothesis is the switch that was flipped to the start position only once, setting everything in motion in the particular direction we call forward. Without this single, extraordinary fact about the beginning, nothing else makes sense. The relentless increase of entropy, the formation of memories, the unbreakable chain of cause and effect, all of these temporal asymmetries emerge from the combination of two ingredients. The first is the statistical dynamics, the laws that tell us disorder is overwhelmingly probable. The second, and absolutely critical, ingredient is that one-time, low-entropy boundary condition in the distant past. The past hypothesis is the anchor for the arrow of time. It tells us why we remember the Big Bang and not the heat death. Our past is special because it connects to the special state. This reframes the entire mystery in a startling new light. For centuries, the puzzle seemed to be, why does entropy always increase? Boltzmann gave us the statistical answer. But that answer only works if we assume the universe started in an unlikely state of low entropy. So the deeper, more profound mystery is no longer about the flow itself, but about the source of the flow. Why did the universe begin in such a specific, improbable, and exquisitely ordered configuration? The smooth, hot density of the Big Bang appears not as an answer, but as the question we must now confront. The past hypothesis does not solve the riddle of time, it perfects it, sharpening our focus onto the very first moment of all. What could possibly account for a beginning that defies the statistical odds so completely? This ultimate reliance on a one-time special beginning leads us to a truly mind-bending paradox, one that reveals just how precarious our understanding of reality might be. If the universe lasts for an eternity, or if it is infinite in size, then the statistical rules of thermodynamics make an astonishing prediction. Given enough time, anything that is not strictly forbidden by physics, no matter how improbable, will eventually happen by random chance. This includes the spontaneous formation of complex, ordered structures from the chaos. In a near-equilibrium universe trillions upon trillions of years into its future, a sea of uniform, lukewarm particles will still experience tiny quantum fluctuations. Most of these are insignificant, little ripples that appear and vanish. But if you wait long enough, an unfathomably long time, a fluctuation could occur that is not tiny at all. By pure random accident, a vast number of particles could spontaneously arrange themselves into any configuration you can imagine. They could form a perfect replica of the Eiffel Tower, or a living, breathing giraffe, or even a fully formed, self-aware human brain, complete with a lifetime of detailed, coherent memories. This theoretical entity is known as a Boltzmann brain. It would flicker into existence, conscious for just a fleeting moment, believing itself to be a person with a past and a future, only to dissolve back into the featureless void an instant later. All of its memories, its sense of self, its entire perceived reality, would be an illusion, a cosmic accident with no connection to an actual past. According to raw probability in an eternal, static universe, such a disembodied, self-aware fluctuation is actually far more likely to occur by chance than an entire, ordered cosmos like ours. Why? Because it is a smaller, less complex fluctuation. It is statistically easier for particles to randomly arrange themselves into a single, isolated brain with false memories than to arrange themselves into the entire low-entropy beginning of a universe that then evolves billions of galaxies, stars, planets, and billions of real brains over billions of years. The absurd, unsettling conclusion is that if our universe were simply an eternal, high-entropy soup, beings like us, with consistent memories and an apparently long history, should be incredibly rare. The vast majority of conscious experiences would be those of fleeting Boltzmann brains popping into and out of existence. Therefore, if you believe your memories are real and that you are part of a long, coherent cosmic history, you must also believe you are not a Boltzmann brain. This logical absurdity is not just a quirky thought experiment. Physicists and cosmologists take it very seriously as a powerful argument against certain models of the cosmos, particularly those that posit an eternal or cyclic universe without a definitive beginning. The existence of our ordered universe and our coherent experience within it is powerful evidence that we did not arise from a random fluctuation in an eternal void. Our reality is not a statistical fluke in an endless sea of disorder. The past hypothesis, the fact that our universe began in a state of spectacularly low entropy, is what saves us from this bizarre fate. It provides a foundation for our memories and our history that is not random but causal. The absurdity of the Boltzmann brain paradox ultimately underscores the profound and genuine specialness of our cosmic starting point. It tells us that any complete theory of the universe must explain why the beginning was so extraordinarily ordered, not by appealing to impossible luck, but through a deeper principle that makes such a beginning natural or even inevitable. The story of time's arrow is not one of a single, fundamental law. It is a story of two parts working in a delicate and necessary partnership. The first part is the set of time-symmetric dynamical laws, the reversible equations that govern every particle interaction. The second part, and arguably the more crucial, is a very specific initial condition, the low-entropy state of the Big Bang. Physics has traditionally been a quest for laws, for the elegant rules that dictate how things move and change. But for the arrow of time, the boundary condition, the starting point, is paramount. The laws provide the stage and the actors, but the initial condition provides the script, the one-way direction in which the play must unfold. This realization shifts the entire focus of the mystery. We are no longer asking why entropy increases, because statistical mechanics gives us that answer. We are now asking why the universe began in a state that made that increase possible in the first place. The ultimate puzzle of time is no longer purely a question for thermodynamics or statistical mechanics. It has become a profound question for cosmology and the search for a theory of quantum gravity. Why was the early universe in such an exquisitely ordered, low-entropy configuration? Was this simply a monumental stroke of cosmic luck, a random roll of the dice that happened to land in the one in a gazillion configuration that allows for stars, planets, and life? That explanation feels deeply unsatisfying, leaving the most important fact about our reality to pure, inexplicable chance. Or was it a necessity, the only possible outcome from some deeper, more fundamental principle? Perhaps the smooth, low-entropy beginning is not an accident, but a logical consequence of a theory that describes the universe's very origin, a theory that unites quantum mechanics with gravity. Some proposals suggest that our universe emerged from a quantum fluctuation in a pre-existing realm, but one where the fluctuation naturally produced a low-entropy state. Others explore the idea of a cyclic universe, where each cycle begins with a kind of cosmic reset that establishes a new low-entropy boundary. The search for an answer pushes us to the very edge of our understanding, to the moment before time itself had meaning. The arrow of time, which feels so immediate and personal in every moment of our lives, ultimately points back to a single, inscrutable instant at the birth of everything. Our experience of cause and effect, of memory and anticipation, hangs on the explanation for that first fleeting state of order. The abstract dance of atoms finds its echo in the most ordinary moments of our day. Watch an ice cube left on a kitchen counter. Its sharp, geometric edges begin to blur. Molecules of water, once locked in a rigid, crystalline lattice, gain energy from the warmer air. They break free, transitioning into a liquid puddle that spreads across the surface. The orderly structure of the ice is gone, replaced by a formless pool where water molecules move in countless, random arrangements. This is entropy increasing, the shift from a specific, low-entropy state to a common, high-entropy one. The thermal energy from the room, once concentrated in the air, has become dispersed, shared with the ice to melt it, increasing the overall disorder of the system. Pour a splash of cold milk into a hot cup of coffee. At first, the two liquids are distinct, a swirl of white against dark brown. For a brief instant, you could imagine carefully extracting every milk molecule. But within moments, the swirls blend, diffuse, and vanish into a uniform, tan beverage. The ordered separation is lost. The milk molecules, initially confined to one region, now explore every possible position within the coffee, mixing into a state with astronomically more microscopic configurations. This mixing is a direct, visible signature of the universe's statistical preference, a tiny testament to the arrow of time happening right in your mug. Look at a photograph of yourself from a decade ago. The changes you see, the subtle lines, the shifting patterns, are not just the marks of experience but also of a physical process. Our bodies are magnificent structures that maintain a delicate, localized order against the tide. But this maintenance requires constant work. We consume food, a highly ordered form of low-entropy energy. Our cells break down that complex order, extracting useful energy to repair and build, while releasing waste heat and simpler molecules. The global entropy increase from digesting your meal and radiating body heat far outweighs the local order preserved in your tissues. Aging, in a thermodynamic sense, is the gradual, inevitable loss of that battle, a slow drift of our biological structure toward equilibrium with our environment. Leave a shiny iron nail outside in the rain. Over time, a reddish-brown crust forms on its surface. This rust is iron oxide, a more chemically stable and disordered state than pure iron. The nail, in its metallic form, represents a specific, organized arrangement of atoms. Exposed to oxygen and water, those atoms react, forming a brittle, flaky compound. The process releases a small amount of heat, dispersing energy. The strong, unified structure gives way to a crumbled, oxidized one. The transformation is slow, but its direction is certain, another quiet victory for entropy in the background of our world. Light a log in a fireplace. The dense, solid wood, full of complex cellulose molecules, reacts with oxygen in a fiery release. The log vanishes, transformed into gases like carbon dioxide and water vapor, a pile of ash, and most importantly, a brilliant rush of light and heat. The concentrated chemical energy stored in the wood's bonds is liberated and radiated out into the room, warming the air and the stones, eventually dissipating into the night sky. The orderly structure of the log is gone forever, replaced by dispersed particles and radiant energy that will never spontaneously reassemble into timber. A burning fire is perhaps the most primal and visceral example of the irreversible arrow, a one-way conversion from concentrated fuel to diffuse warmth. Even the most stunning examples of growing order, like a seed sprouting into a towering tree or a child growing into an adult, obey the same universal rule. These are not exceptions. A tree is a local island of immense complexity, but it builds itself by consuming low-entropy sunlight. The sun's core is a massive reservoir of ordered nuclear fuel. Its fusion reactions produce high-energy photons that travel across space. When a leaf captures that photon, it uses the energy to build sugar from carbon dioxide and water, a process that releases heat and increases the disorder of the surrounding environment. The tree's growth represents a local decrease in entropy, but it is purchased at the cost of a far greater entropy increase in the sun and the Earth's atmosphere. Every living thing is a temporary eddy in the great river of disorder, sustained by consuming order from elsewhere and paying for it with interest in dispersed energy. So the next time you see steam rise from your coffee or notice a new crack in an old sidewalk, you are witnessing the same fundamental principle that guides the expansion of the cosmos. The arrow of time is not hidden in distant galaxies, but written into the fabric of every simple, everyday change. Yet within this relentless tide toward disorder, a flicker of the opposite seems possible. The laws of physics are reversible, so statistically, shouldn't we occasionally see entropy go backwards? The answer, revealed by cutting-edge modern physics, is a cautious yes. We can, in fact, witness entropy decrease, but only under the most extraordinary and fleeting circumstances. This is not a violation of the second law, but its deepest confirmation. The key lies in a set of powerful results known as fluctuation theorems. These are not mere thought experiments. They are precise mathematical formulas that calculate the exact probability of observing a temporary decrease in entropy in a small system over a brief period of time. They tell us that if you watch a tiny enough piece of the universe for a short enough span, you will occasionally catch it behaving in a way that seems to defy the arrow of time. It is like watching a single droplet of water in a vast waterfall momentarily leap upward against the current. The theorems quantify exactly how unlikely that leap is, depending on its size and duration. This probability falls off exponentially, meaning even a small decrease in entropy becomes astronomically rare incredibly fast. To actually see this, scientists had to build experiments that could track the motions of individual particles. One famous study used a microscopic plastic bead, a colloidal particle, held in place by laser beams creating an optical trap. The researchers watched as the bead was jostled by the random kicks of water molecules, a process called Brownian motion. Most of the time, the bead's motion increased the entropy of its immediate environment, as expected. But by analyzing millions of tiny trajectories, they found the rare, precious moments. On occasion, for a fraction of a second, all those random molecular kicks would coordinate, just by sheer chance, to do something remarkable. They would push the bead in such a way that it actually absorbed heat from its surroundings and performed a tiny amount of useful work against the laser trap, effectively decreasing the local entropy. These were the entropy-reducing paths predicted by the fluctuation theorems, captured in real data. These events are vanishingly rare, incredibly small in scale, and over in an instant. They do not and cannot scale up to make a broken glass reassemble or a gas unmix itself in a room. What they do is far more profound. They prove that the second law of thermodynamics is truly statistical, not absolute. It is a law of overwhelming likelihood, not an unbreakable commandment. The universe allows for backward steps, but they are so brief and so improbable that for any system of meaningful size over any human timescale, the forward march is all but certain. These fleeting reversals are not ghosts in the machine. They are the quiet whispers of the underlying reversible laws, reminding us that our arrow of time is painted in probabilities, not carved in stone. This fleeting glimpse of time running backwards in a lab only sharpens a more intimate mystery. We feel time, not as an abstract increase in disorder, but as a palpable flow, a river carrying us from a fading past into an emerging future. We live in the vivid, undeniable experience of the now. This present moment feels like a moving spotlight, illuminating what is real and leaving the past in shadow. Yet, our most successful theory of the cosmos, Einstein's theory of relativity, paints a radically different picture. In the block universe model of eternalism, past, present, and future are not sequential. They all exist equally real, laid out together in a single, four-dimensional structure called spacetime. Your birth, you listening to this, and every moment of your future are all just fixed points in this vast, unchanging block. There is no privileged now that moves. From this God's eye view, time is just another dimension, like space. Saying an event is in the past is no different from saying it is to your left. The flow is an illusion. This creates a profound tension. If the arrow of time is just entropy increase and the universe is a static block, what is this powerful feeling of passage? Why do we feel trapped in a moving present? One compelling suggestion is that consciousness itself is a process that requires the thermodynamic arrow. Your brain is a physical system. To think, to feel, to be aware, it must process information. Neurons fire, signals travel, memories form. As we've seen, every one of these actions is an irreversible event that increases entropy. The sensation of a flowing now may be the conscious experience of this continuous, entropy-generating computation. You are not moving through time. Instead, your awareness is a sequence of brain states, each one a record of the just prior state, each one creating the feeling that a moment has just passed. The moving spotlight is the light of consciousness itself, powered by the relentless thermodynamic engine of your mind. Yet this only reframes the puzzle. It explains how we experience time's direction, but not why that experience feels like a continuous, unified present. The hard problem of consciousness meets the hard problem of time. Is the now a fundamental feature of reality that physics hasn't yet captured? Or is it truly a beautiful, persistent illusion generated by a brain processing the universe's one-way story? This remains one of the deepest mysteries, where the physics of the cosmos meets the intimate reality of being. The feeling that time is a one-way street has fueled countless dreams of turning back the clock. But if the arrow of time is woven from statistics and entropy, what does that say about the possibility of time travel, especially to the past? Some solutions to Einstein's equations of general relativity, do allow for strange geometric structures called closed time-like curves. These are theoretical pathways through space-time that loop back on themselves, essentially creating a time loop. An object following such a curve could, in principle, return to its own past. This is not science fiction, but a mathematical possibility within the theory. Yet these solutions come with enormous physical problems, often requiring exotic forms of matter with negative energy, conditions we have no evidence exist in our universe. More troubling are the logical paradoxes they invite. The most famous is the grandfather paradox. If you travel to the past and prevent your own grandfather from meeting your grandmother, you would ensure your own birth never happens, which means you could never have traveled back in time to interfere in the first place. This creates a logical inconsistency, a loop of cause and effect with no clear origin. Physics abhors such inconsistencies, and many theorists believe the universe would find a way to prevent them, perhaps through quantum effects that make the journey impossible. But there is an even more fundamental, and perhaps more decisive, obstacle rooted not in geometry or logic, but in thermodynamics. To travel to the past is to travel to a moment when the universe's entropy was lower. You would be moving from a present of higher disorder to a past of greater order. Your very presence in that past, along with your memory of the future and the machine that brought you there, represents a massive injection of disorder into that earlier, more pristine state. Think of it like trying to insert a scrambled egg back into its shell. The act of arrival itself would require a staggering, coordinated decrease in entropy on a cosmic scale. All the particles that make up you and your technology would have to be meticulously arranged to appear in that past moment, a statistical miracle of unimaginable proportions. It is not just unlikely, it is forbidden by the same overwhelming odds that prevent a gas from spontaneously unmixing. The thermodynamic arrow does not just describe time's flow, it enforces it. It may be the ultimate cosmic law that makes time travel to the past not merely technologically daunting, but statistically impossible. The universe's relentless drift toward disorder builds a one-way wall between the present and the past, a wall no machine could ever breach without reversing the very story of creation. The arrow of time points relentlessly away from a single, extraordinary fact. Our universe began in a state of spectacularly low entropy. This is the ultimate boundary condition, the past hypothesis, and it is the one thing our elegant statistical story cannot explain. It is the unsolved mystery at the heart of everything. Why was the cosmic starting point so exquisitely ordered? Cosmologists have proposed several speculative yet compelling ideas. One leading candidate is cosmic inflation. This theory suggests that in the first fraction of a second, the universe underwent a period of exponential expansion, stretching a tiny quantum patch of spacetime into the vast cosmos we see. This process would have ironed out any wrinkles, smoothing the distribution of matter and energy to an incredible degree. Inflation does not so much explain the low entropy as it pushes the question one step back. It tells us how the smoothness was achieved, but we must still ask why the conditions before inflation were so special as to allow that smoothing to happen in the first place. Another idea looks to the quantum vacuum itself. Could our entire universe be a rare but possible fluctuation from a pre-existing eternal void? In this view, the Big Bang was a quantum tunnel from nothingness into something, a bubble of spacetime that spontaneously nucleated. The challenge here is probability. A fluctuation that produces a smooth, low-entropy universe as large and long-lived as ours is astronomically unlikely compared to a tiny, short-lived bubble of disorder. To make this work, theorists must find a principle that makes our kind of beginning not a freak accident, but a natural outcome. Perhaps the most poetic proposal comes from physicist Roger Penrose. His conformal cyclic cosmology envisions an endless sequence of universes, or eons. In this model, the far, far future of our universe, the heat death where all matter has decayed and only massless particles like photons remain, undergoes a profound transformation. At this point of maximum expansion and uniformity, the universe loses all sense of scale. Distances become meaningless. Penrose argues that this smooth, empty, infinite state can be mathematically reinterpreted as the high-density, low-entropy beginning of a new eon. The heat death of one cycle becomes the Big Bang of the next through a mathematical rescaling called a conformal transformation. In this view, the low entropy of our beginning is not an accident, but a consequence of the specific way the previous eon ended. It is a cosmic cycle of renewal, not of matter, but of the very conditions for time itself. Each of these ideas is a bold stroke on a vast canvas, but none is yet a complete picture. They all point toward the same profound need. A full understanding of why time has an arrow, of why our past is so special, likely requires a theory that does not yet exist, a theory of quantum gravity. This would be a framework that successfully marries the large-scale physics of general relativity with the small-scale weirdness of quantum mechanics, a theory capable of describing the very first instant when the universe was both infinitely dense and governed by quantum uncertainty. Only within such a theory might we find a principle that makes a low entropy beginning not a mysterious postulate, but an inevitable derivation. The arrow of time, which feels so personal and immediate, ultimately asks us to solve the deepest puzzle of all, the origin of the cosmos itself. All these arrows point in the same direction, but only one is the river itself. The thermodynamic arrow, the relentless increase of disorder from a low-entropy past, is not merely one arrow among many. It is the master arrow, the fundamental flow from which all other temporal asymmetries emerge. Think of the universe's timeline as a landscape carved by water. The low-entropy state of the Big Bang is the mountain spring, the singular source. The statistical tendency for entropy to increase is the water itself, the river's flow. And as that river carves its way through the cosmic landscape, it creates all the features we recognize as time. The psychological arrow, our stream of consciousness and memory, is like a boat carried by the current. It cannot go upstream because the flow of entropy provides the very energy for the brain's processes, etching each memory as a permanent marker of the river's passage. The causal arrow is the shape of the riverbed defined by the water's one-way journey. Effects are always downstream from their causes because moving against the current would require a miraculous, coordinated decrease in entropy, a statistical impossibility for any meaningful event. Even the cosmological arrow, the expansion of space, is not the river but the widening valley through which it runs, a grand feature that enables the river's long and complex journey but does not dictate its direction. All these phenomena are not separate mysteries. They are different perspectives on the same fundamental story, the universe's statistical journey from a rare and special beginning toward a probable and generic future. We do not experience multiple times, we experience one time, one narrative viewed through different lenses. When we remember, we are tapping into the entropy gradient of our own neural history. When we witness a cause leading to an effect, we are observing a local cascade of increasing disorder. Our entire reality, from the formation of a galaxy to the feeling of a moment slipping away, is a single, coherent expression of this principle. The smooth beginning set the stage, and probability has been writing the script ever since, with every irreversible process a sentence in the story. This synthesis resolves the paradox we began with. The universe's laws are reversible, yet time has a clear direction because the initial condition was profoundly asymmetric. The symmetrical laws provide the rules of motion, but the past hypothesis provides the only starting point that makes a story possible. Without that low-entropy spring, there would be no river, no carving of channels, no journey at all. just a static, featureless plane of equilibrium where the words past and future have no meaning. Our existence within the flow, our ability to ask these questions, is the most compelling evidence that we are part of that story, carried along by the deepest current in the cosmos. The deepest mystery of time is not found in its flow but in its source. We have journeyed from the shattering of a glass to the birth of the cosmos, and a single, elegant story has emerged. The fundamental laws of physics, from the quantum realm to the curvature of space, are perfectly symmetrical. They do not distinguish between past and future. Yet our reality is saturated with a one-way arrow. This arrow is not written into those laws. It is painted onto the universe by statistics, by the overwhelming probability that systems will move from order to disorder. This is entropy, the universe's relentless drift toward its most probable arrangements. But for that drift to define a direction, it needed a starting point of profound improbability. It needed the Big Bang, a moment of exquisite, low-entropy smoothness. From that singular beginning, the statistical tide could flow in one consistent direction, carving the channel of time itself. Our memories, our sense of cause and effect, the very expansion of space, are not separate phenomena. They are all manifestations of this one great unraveling from cosmic order to cosmic disorder. The flow of time is not a fundamental feature of reality. It is an emergent property, a story told by countless particles collectively exploring probability, guided by an initial condition of breathtaking simplicity. This realization transforms our view of existence. The breaking of an egg, the fading of a memory, and the cooling of stars are all chapters in the same epic, a narrative that began with the first flash of light and will continue until the last whisper of heat dissipates into an endless night. Understanding this does not diminish time's mystery, it deepens it, connecting the most intimate moments of our lives to the grandest architecture of the cosmos. If you found this exploration of reality's one-way street compelling, please consider liking this video and subscribing to the channel. It helps immensely in bringing these profound mysteries to light. And in the comments below, let us know which other deep puzzle of physics you would like to explore next. Thank you for watching.